Okay, I'll be solving the numericals on small signal common source MOSFET, enhanced a metal oxide field effect transistor amplifier. So the device that is used for as an amplifier is MOSFET in common source configuration. Contents of this session: problems on field effect transistor, problems on MOSFET, problems on biasing of MOSFET. So it includes the biasing circuit, self-bias, and a voltage divider bias. So field effect transistor, consider a small problem, relate the problem, calculate the input conductance for a junction field effect transistor having a device parameter ID SS is equal to 15 milliamperes and a pinch of voltage as minus 4 volts. So GM0 is given by the relation, input transconductance is given by the relation 2 IDSS upon the absolute value of the pinch of voltage. So that goes to give you an answer of 6 millisiemens or 6 millimho. Next, field effect transistors, second problem. Determine the pinch of voltage of a junction field effect transistor with a GM0, that is a conductance, input conductance of a 10 millisiemen and a drain current, drain saturation current as 12 milliamperes. So GM0, you utilize the relation GM0 is equal to 2 times IDSS upon VP. Find out the pinch of voltage by using this relation, and it comes out to be 2.4 volts. Field effect transistor, once again, third problem over here. What is the value of IDSS if VP is equal to 2.5 volts? Here we'll take the overall current. So GM is equal to 2 times IDSS by VP into 1 minus VGS 0 upon VP. So here VGS 0 is given to be minus 1 volt. So calculate the current of IDSS, and it is estimated after calculation to be 12.5 milliamperes. Now we are moving into MOSFET. So MOSFET, drain feedback configuration. First we'll solve how to calculate the value of input conductance for MOSFET field effect transistor. Here VG threshold voltage between the gate and source is given to be 3 volts, and it is biased at VGS is equal to 8 volt. So the dynamic resistance K is equal to 0.3 into 10 raised to 3. So substitute in this relation GM is equal to 2K into VGS 0 minus VTH. Substitute in this all the parameters, that is K, VGS 0 and VT, and you will get the answer as GM is equal to 3 milliseconds, Siemens. A common source, a self-bias MOSFET. First, doing the analysis, both AC and DC, first you have to identify the type of biasing network. So it is a self-bias network. Knowing the type of biasing, find out the DC analysis, that is, it includes the input voltage VG, then the output voltage VD, and so on. So first find out GM. So GM is equal to 2K into Vgs 0 minus Vt. So GM comes out to be 3 millisiemens. RD is given from the data sheet, and or it has to be provided by the person who is giving the problem. So RD is equal to 100 kilo ohms. Calculate GM as given in example 1. It is done aside. So input impedance Zi is equal to, use a relation, direct analytical relation, substitute it in the analytical relation. So Zi is equal to RF plus RD, small rd dynamic resistance, parallel resistance across the drain terminal, upon 1 plus input conductance into dynamic resistance, a parallel combination of dynamic resistance and resistance across the drain terminal. So Zi comes out to be 1.345 mega ohms, which is quite high, very high. So output impedance Z0 is a parallel combination of RF parallel RD, parallel dynamic, parallel the resistance across the drain terminal. So Z0 is equal to 2.15 kilo ohms. Voltage gain AV is minus GM into the combination of the resistances available at the output port, that is RF parallel dynamic resistance, parallel resistance across the drain. So it comes out to be minus 6.45. Voltage gain is very low for self-bias circuit. Self-bias E MOSFET. Repeat the problem given if K is changed to 0.2 into 10 raised to minus 3 and compare the results and determine the input impedance, output impedance and voltage gain for the amplifier if K is equal to 0.3 into 10 raised to minus 3. So GM is equal to 2 milliseconds. Input impedance, by using the same relation, it comes out to be 1.887 mega ohms, whereas when GM was something 3 milliseconds, that time it had come down to, it was very high, 3.45 mega ohms. So Z0 is equal to RF parallel RD, which is equal to 2.15, and almost same when GM was equal to be 3 millisiemens. Voltage gain is minus 4.3 and it has reduced down if you are comparing it when GM was equal to 3 millisiemens. Let us compare that. So comparison table, when K is varied from 0.3 to 0.2, input impedance was 1.345 mega ohms. When K is equal to 0.3 into 10 raised to 3, and when K is equal to 0.2 into 10 raised to 3, that time it became high, that is 1.88. Z0 remains same, voltage gain has reduced. So inference is that input impedance increase, voltage gain becomes more negative, and if it is becoming more negative, the device is pushed into saturation region from the active region. Next, voltage divider common source E MOSFET amplifier. So here E MOSFET configuration is given. So before going to any analysis, what you have to do is first determine the stability of the configuration given to you. So here two sets of values are given, that is Vi is equal to 0.8 millivolts and the dynamic resistance is 40 kilo ohms. So based on this, you are going to do the ahead analysis, both DC as well as AC. You look at the ideal network of the device, it is an N-type E-MOSFET. Z0 is equal to dynamic resistance and parallel the resistance offered by the drain terminal. This calculation you will calculate. So voltage gain is GMRD. We are writing in general this time. So no specific values. GMRD. Why? Because RD is a dynamic resistance is greater than 10 times the resistance across the drain terminal. So from the data sheet now pick up the values what are required. So K is equal to 0.4 into 10 raised to 3. Then get to source threshold voltage is 3 volts and get to source voltage is equal to 0 volts. Substitute it, get the value of GM is equal to 1.2 millisiemens. Voltage gain, calculate GMRD. So here it comes out to be, it should be minus. So minus 3.96. Minus 3.96. So voltage divider E-MOSFET, again we are comparing, trying to see this voltage gain, how it has come. If we know the two parameters, that is the voltage gain and the output voltage, what, or if we know the input voltage and the voltage gain, what will be our output voltage? So V0, use the relation, V0 is equal to A times Vi and calculate the answer and find out the answer. So end of session.